Hi, everyone. My name is Timur Rashid. I'm the Chief Business Development Officer at Redis Labs. Thanks so much for joining this session. In today's session, we're going to be talking about low latency fraud detection and prevention. And I'll be also joined by a good friend and recognized industry expert, Sid Anand, who's the Chief Architect at DataZoom. Now, some of the objectives of this session are really to understand the importance of fraud prevention, and in particular, with the rise of digitization and digital transformation, how important fraud prevention has become. We'll talk about some of the first principles that lead up to real-time data and fraud prevention. And in particular, we'll take a look at some technical merits that in-memory databases provide, in-memory databases such as Redis. As companies think about building solutions around fraud prevention, there are a variety of key components and capabilities that need to be thought of. And I'll talk a little bit about that. And then finally, I'll transition it over to Sid, who's going to talk about some industry examples, particularly with a focus on email fraud and payment fraud, and he'll share some best practices as well. So without further ado, let's talk a little bit about the State of the Union and the agenda here. We'll talk about the need for real time, we'll talk about first principles, we'll look at the modern architectural components, and then finally we'll talk about best practices. A little bit about me. So I lead business development for Redis Labs with a particular focus on emerging businesses. And my particular focus these days is the application of Redis technologies as it relates to AI and machine learning. Prior to my time at Redis, I spent about 3 years at Microsoft, where I led the global customer success teams focused on Azure. And prior to that, I spent about a decade at Amazon Web Services, where I largely led business development for the company. All right, well, let's talk a little bit about how widespread fraud has become and continues to rise. I mean, if you look at some of the survey results, in particular this one that came from PwC, there's about a 49% increase of companies that experience fraud. And in 2020, it was recorded about $42 billion worth of losses that were caused by fraud. And year over year from 2019, banks actually reported about a 17% increase in the total cost that fraud incurred for those banks. In another study, online fraud really accelerated during the pandemic. And many of you that are familiar with this space have many data points to be able to show for this, but about 79% of respondents in this particular survey said they saw an increase in fraud as of November 2020. And in fact, 90% of these respondents have said they expect fraud to increase over the next 12 months. And when you look at cyber fraud, payment fraud, and even identity theft, all those areas are largely being exploited because systems don't have the ability to necessarily catch and very quickly respond to some of the fraudulent behavior. And in fact, when you look at existing solutions today, they're really not built for the digital economy, or they're suboptimal in the abilities and capabilities that they provide. So oftentimes you hear about systems being slow, inefficient, and expensive. And it's with those challenges that many companies have related to fraud that you have to think about first principles when approaching this particular problem space. Modern fraud detection solutions need to be based on first principles. And I really like this first principles thinking because it helps really help companies solve the problem at the root cause. And so what are some of those first principles that are needed for a fraud detection solution? Number one, it's got to be real time, right? The nature of fraud is you want to be able to catch it as quickly as you can. And given the amount of data that goes in preparing machine learning models and capabilities to detect and prevent it, the truth of the matter is there's so much data in real time that needs to be factored into these models that the more agile and low latency you can have in being able to detect it and solve for fraud, the better off you'll be as a business. Secondly, they need to be AI and machine learning driven. It's not only the ability to predict what may happen, but it's also the ability to learn from the various inputs that come in real time. And then finally, the systems need to be integrated. And if you think about those first principles, you often need to figure out what technology can enable all three of these first principles to be part of your foundational layer. And this is where I'd really like to talk about Redis as a technology. When you look at Redis, which is an in-memory database, it offers a variety of native capabilities and a variety of what I like to call more composite or complex capabilities that help meet the needs of a modern architecture for fraud prevention and detection, right? So at the core, Redis offers, core data structures such as hashes, strings, lists, bitmaps. Some of those native data structures that, if stored in memory, you can leverage the benefits of low latency. Secondly, when you actually look at some of these more complex and value-added capabilities, Redis, in particular, Redis Enterprise, has enabled a bunch of these modules. And think of these more of complex data types, such as search data or graph-based data, or even time series data, which has a lot of applicability in the case of being able to efficiently manage a fraud solution. Or AI, being able to take the ability of bringing AI models closer to the data. And then finally, when you look at some of these core capabilities of being able to scale, globally distributed in-memory database, this is where Redis Enterprise offers a variety of these capabilities, from linear scaling, high availability, durability, geo-distribution, and a variety of other things that we at Redis Labs have learned through the experience of managing Redis at scale for over a decade and being able to infuse them in product-specific features and capabilities. So when you look at the technical merits of Redis as an in-memory data store, what you can really see is now you have capabilities that can be largely implemented to meet the business outcomes of a fraud solution. So going into that, if you translate the first principles into actual outcomes, there are three specific areas that are of interest. Number one, being able to update digital identities in real time. Now, if you think about machine learning models that can be built on predefined data, you can build those models and definitely deploy them in the cloud and largely do machine learning and predictions based on that data. But there's a variety of new data that comes from user input, constant changes that may happen. And in fact, with fraudulent actors, there's a variety of ways that they can mask their identity, change the location of where they are to actually, play against a fraud detection system. So the importance of being able to do real-time updates for the digital identities is extremely important. Secondly, being able to increase the efficiency and detection speeds at which these AI models operate is equally important, right? There's constant changes going on, and like I mentioned, there's a lot of new user input that's coming in that have not been factored into the pre-built models that you've trained. And therefore, being able to quickly respond to that while being able to also drive more accuracy will ensure that the machine learning models that have been built and deployed are accurately catching those fraudulent activities that have both been, planned for, but at the same time unplanned for. And then finally, when you look at the high-speed statistical analysis that can be done based on the data over historic time, or being able to look at various things such as graph-based data and relationships between a particular user or a consumer and the various things that they're connected to, really help companies reduce cost. Now, I really want to drill into the specific examples. So when you actually look at keeping digital identities updated in real time, I specifically want to focus on the capabilities of search and graph. When you actually look at it, consumers expect a very responsiveness with their digital experience, whether that's through mobile, web, or any other sort of digital medium. The Redis search technology and Redis graph technologies basically take common search data types and graph data types, infusing them in the database to be able to take a look at, for example, geolocation data and identity searches, which can actually influence the scoring of an identity. And for that matter, even looking at graph data, how does a consumer relate to the various connections within their social graph, for example, or within specific digital identities characteristics that can be factored into the model. And ultimately, being able to search in a very fast way and being able to accurately look at graph relationships, one can update digital identities in a way in real time that they can really help catch fraudulent activity. Now, secondly, when you combine that with the ability to increase the accuracy of detection, this is where it's so important to be able to bring the data model, or in fact, the machine learning model, whether it's built in TensorFlow or PyTorch, and being able to deploy that model closer to the data so that the latency is reduced significantly. In fact, we're talking about sub-millisecond latency in some use cases of fraud detection, which can cost companies millions, and in fact, the industry billions of dollars if you can really increase the speed at which you can detect these things and the accuracy as well too. And this is where being able to leverage the machine learning models directly where the data lives is extremely of paramount importance. And the high accuracy and the speed at which companies can detect these things really comes down to the bottom line. And thirdly, when we look at reducing detection costs with statistical analysis, this is where the capabilities of time series analysis and being able to look at pattern matching through probabilistic data structures such as Bloom filters really strengthens the overall posture and value proposition of a given fraud detection solution. And this actually transcends it from rule-based fraud detection to a point where you can actually leverage time series data, you can leverage pattern matching, and by being able to do that effectively, companies can really reduce the cost at which they operate their overall systems. When you take all three of these capabilities and kind of put it all together, this is where you have a modern architecture for fraud detection and fraud prevention. And starting from the left-hand side here, you can see whether that's transactional information that's coming in, or inputs from behavioral biometrics, or even customer identity. You can take all those capabilities and then map them across streaming data, search specific data, Bloom filters, AI and machine learning models, and then even to the point of leveraging time series data to really be able to accurately go and do real-time transaction scoring, digital identity validation, and anomaly detection. And within this architecture, you have all these components that can really strengthen the overall capabilities of a fraud prevention and detection solution. Now, with those first principles in mind and the specific examples of real-time identity updates, being able to leverage AI and machine learning so that you can drive more accuracy and speed with the machine learning models, and then being able to leverage search capabilities and things like Bloom filters to do pattern matching, what you effectively have is a modern architecture to meet those needs. This is where I'll pass it over to Sid, who's actually going to look at some industry examples around email fraud and payment fraud and share some best practices when being able to implement them, which very much relate to some of the key first principles that I've identified earlier in this presentation. So now I'll turn it over to Sid. Thanks so much.
Thank you, Tamer. A little bit about me. I've worked in the Bay Area for about 20 years at a variety of companies. I'm currently the chief architect at DataZoom. Before joining DataZoom, I was the chief data engineer at PayPal, and I also worked at a company called Agari, which is a spearfish prevention company. Today, I'll be talking to you about the work I've done at these two companies. Let's start with email fraud. What is it? The most common form of email fraud, unfortunately, is phishing and spam. It's something we are all intimately familiar with. Phishing and spam are a form of what's called volume attacks. In these attacks, hackers send the same email to tens of thousands of email accounts. In order to defend against this attack, you typically install some sort of secure email gateway. A secure email gateway will comb through all of this email and look for common patterns in the content. It will extract these patterns as signatures and deploy the signatures to the SEG fleet so that as new emails come in that match that pattern, they will be filtered out. So SCGs are extremely good at handling volume attacks. Another type of attack is called spear phishing. Unlike phishing, spear phishing is not a volume attack. Hence, these emails often bypass SEGs. In spear phishing, hackers target a high-value person with a few emails and a bit of social engineering. Let's have a look at some real-world examples. A very common one around tax time is called the W-2 spearfish. In this example, cyber criminals pretend to be executives at a company, email payroll officials asking for employee W-2s. Once they receive those W-2s, they file fraudulent tax returns within days and receive tax refunds to their own accounts. Let's have a look at how Agari battles spearfish. In this example, Agari's collector is deployed at an enterprise customer, customer A. As emails flow into enterprise customer A, the customer holds the email and the Agari collector extracts metadata such as the email headers and sends it to Agari Cloud. In the Agari Cloud, an ingester process will validate the content and normalize it if necessary, and send it on to a process called the scorer. The scorer's job is to use a set of models to determine whether or not this email is fish or not fish. Sometimes it doesn't have enough information to generate a high quality score. If that happens, the scorer will forward the message to an online model builder, which will rebuild a model, including some new information that it has, to generate a higher quality or higher probability confidence score. Regardless of which path it takes, the scorer or the online model builder will forward this data to the alerter, which will then send a verdict of fish or not fish to the Agari collector. Once the Agari collector receives this, based on some policy that has been defined, it will decide whether or not to quarantine this email, log it, or perhaps label it or forward it on as allow it as an okay email. This entire process takes 3 seconds for the majority of messages. Now, it is very important that this entire process is fast because the customer is buffering a ton of email. We don't want the customer to run out of disk space or memory. So if the customer doesn't receive a speedy response, in most cases, it will fail open and allow the message into its domain, into its enterprise, and that might put some of its employees at risk. We made a ton of decisions to make this entire system fast and efficient, one of which was to use Redis as our data store. Let's see how we use it. So every night, we run Spark jobs to build full models, and we deploy those models along with some metadata, such as the list of features that will be used in inferencing. We load that model metadata and model into Redis. We also load what we call nightly feature digests. So an example of a feature digest would be to get the average number of messages we receive from an email domain on any given day, or over the average per day. This can be used to determine if on a recent day, we receive a huge influx of messages from a domain that typically doesn't send us much. That could be a sign of fraud. As mentioned earlier, if we have to, if the scorer cannot generate a high enough confidence score, it will forward the message to the online model builder. The model builder can then build a model and push it back into Redis, so that the next time the scorer needs to generate a high model score, it will just pull it from Redis. And as traffic flows, we update live counters with on decay variables. An example of that would be traffic from a particular email domain, a sending domain. So again, if today we receive a million emails from a given sending domain that typically only sends a handful. That's a sign that perhaps that system has been taken over by a fraudster. Once all of this data is in Redis, the scorer pulls it down to generate a score. The loads from Redis take typically less than a millisecond. Now that we've talked about email fraud, let's talk about payment fraud. Based on my experience at PayPal and also at eBay, I came across a few interesting use cases. In the first one, a seller sells thousands of inexpensive trinkets in order to raise the seller's rating, to boost their reputation. And then after a while, they sell some very high-priced items, but don't deliver them and run away with the money. Another case of scams that I've seen are like the overpayment scam. So a fraudulent buyer overpays for an item and then asks the seller for a refund to a different account than the one he paid from. After receiving the overpayment amount in that account, the buyer claims an account takeover when talking to PayPal. PayPal will respond by refunding all of the money. Therefore, the fraudster made away with more money than he paid for the item. Last but not least, we have a collusion network. In a collusion network, we could have both a fraudulent seller and buyer. There is actually no item that ever is sent between the two of them. They just list a false item, say on eBay. After the buyer pays the seller cashes out, and then the buyer claims non-delivery of item so that PayPal will reimburse them. In this case, the buyer and seller double their money. Let's have a look at how PayPal prevents fraud in cases like these. Now, PayPal, you may not know, is not just a payment service. It is made up of buyer credit, merchant credit, peer-to-peer payments, B2C payments. It also does payment processing for companies like Uber. So there are many users with different use cases that talk to PayPal through its web interface or APIs. If one of these services needs to get a risk assessment, it will make a call to the PayPal Risk Service platform. The PayPal Risk platform handles more than 250 million calls a day, with most calls occurring in less than 50 milliseconds. The first service that they'll encounter is the API gateway. The API gateway's job is to route traffic to the correct endpoint based on what is being asked. For example, calls for credit risk assessment may go to a different endpoint than calls for, say, B2C checkout. The layer below that is a rules engine that is used for decisioning. The basic idea here is that this is the layer that generates scores, and the scores are composed from models that are computed at the layer below it. So for example, if there's a credit risk assessment, like someone is applying for, let's say, a credit card, and PayPal has to decide whether or not to grant a credit card, it may run, for example, an account takeover model, and it may also run a credit risk model, and the decision layer will combine these into a score and return it in the response. Last but not least, we have the risk data platform. Let's have a closer look at that. So in the risk data platform, we typically run a nightly batch job every once a day to scan data in Hadoop, HDFS, and Teradata. Over the last 20 years of operation, PayPal has amassed over 150 petabytes of transactional data and other metadata that it uses in these models. So the Spark jobs basically run through this data, train models, and then push the models plus metadata into Aerospike. Similarly, or similar to the case I talked about earlier with email fraud, PayPal also generates nightly feature digests. So in the case of payment fraud, it could be the average purchase price for a buyer or seller, or it could be the average riskiness of a purchase, in the last 6 months for the buyer or seller. And that data will be stored to compare against any recent purchase in order to determine if there's an anomaly. In addition to those data sets, we may also capture recent events, so events since the last model build or feature digest push. So these events could be things like, did you recently change your email or your shipping address? And of course, anytime somebody checks out or transfers data or transfers money, anytime that happens, the risk platform will actually store these recent purchases in Aerospike as well. So let's put it all together and see how it works. Let's imagine that we have a buyer named Bob, and he wants to buy 500 GPUs. So he will contact, or he will use, the PayPal app or check out on some of the PayPal properties or at a merchant, and PayPal risk service will get that request. In addition, we will get his IP address, and it may turn out that this is a foreign IP address. We will then look at recent changes in his account, and we may notice that he's changed his shipping address and his email address. Last but not least, looking at his historical data, we may find that he regularly bought dog food once a month. So this purchase of 500 GPUs seems a little bit suspicious. It may be the case that he gets flagged as an account takeover target, or basically his account was taken over. Now that we've covered both email and payment fraud, I'd like to leave you with some closing thoughts. In both of these cases, speed, scalability, and availability are critical to fraud detection and prevention system viability. When one of these systems is down, the client needs to decide whether to fail open or to fail closed. Clients that fail open incur fraud loss and potential brand impact. Clients that fail closed cause user friction because their online checkout would have failed, or their money transfer to a family member that relies on it will fail. It is critical that these systems rely on high performance databases like Redis and Aerospike in order to keep the client from making such a difficult decision.